Good afternoon, ladies and gentlemen. First of all, I would like to thank the chair of the conference for giving us this opportunity to present our paper. I'm Bhairavi Premnath, and on behalf of the authors, I would like to introduce our paper, an investigation into the primary and subharmonic resonances of the swing equation. This work has been carried out since I started my PhD in mathematics at University of West London under the guidance of Dr. Anastasia Sofroniou just over a year ago. So this paper is an expansion of the prior work, and it builds up on the conclusion towards analyzing the subharmonic resonance. It examines mainly the subharmonic resonance and focuses analytically and numerically the development of oscillatory periodic solution, whereby increasing the control parameter leads to cascade of period doubling bifurcations, and then we see the losing of stability in the system. So in this paper, we also explain the primary and subharmonic resonance through the basins of attraction diagrams and bifurcations. So stability in a power system is closely tied to the concept of disturbances, which are sudden or sequential changes. So even a small disturbance can have a large and interesting effect on the dynamics of a system. So linearizing this equation that represent a system undertaking eigenvalue and frequency methods to analyze the stability of the system can be employed. So in this study, a single freedom of degree system is considered that will allow us to study about the nonlinear dynamics and about the stability of the system in hand. So the study also focuses on the nonlinear aspects of solving a system using methods such as perturbation techniques and also nonlinear methods. Initially in this study, infinite busbar is represented with the assumption of constant voltage and frequency. So if a classical representation of a swing equation is considered, it has fixed voltage which also has a transient reactant. Then the busbar system is reduced to a second order differential equation with constant coefficients. But this equation, however, does not provide novel information. Hence, we consider the analogous form of the swing equation. So this swing equation, which we consider, has parametric and external excitations, allowing for techniques of perturbation theory to be employed. So in our study, we also consider the primary and subharmonic resonances. These two resonances are significant types of resonances that undergoes in a swing equation. So these resonances play a crucial role in analyzing the stability of the system. So the primary resonance is considered to be important when studying the swing equation, and under these conditions, a small amplitude frequency can lead to a large amplitude response if the forcing frequency is close to the natural frequency. So in other words, primary resonance is when the excitation frequency is approximately close to the natural frequency, and the subharmonic resonance is when the excitation frequency is a multiple of the natural frequency. So the swing equation we study is depicted in this figure. So it depicts the motion of rotor of a machine, and the swing equation is formulated accordingly. So considering the damping term, the swing equation that describes the motion of the rotor of the machine is shown in the figure. So we use all three of these equations to study our system. So here the omega r is the constant angular velocity, h is the inertia, Pm is the mechanical power, Vg is the voltage of the machine, Xg is the transient reactant, Vb is the voltage of the bus system, and the theta b is the phase of the bus system. We also consider VB1 and theta B1 to be magnitudes to be small. So after performing some mathematical operations on equation 1, 2 and 3, this following equation is obtained and the alpha 2, alpha 3 terms used in the previous equation is given down. Algebraic techniques such as Taylor expansion and substitution methods are used to obtain this final equation. So the previous slide, the final equation, was used for the perturbation analysis of the subharmonic resonance. So we use a method called multiple scales to find the uniform solution for this equation. And a small dimensionless parameter called epsilon is introduced, which accounts for the effects of damping, nonlinearities, and the excitation frequency, which occur in a specific order. So next, we compare the analytical results with the numerical simulation for the case of the subharmonic resonance. The following figure was obtained, which shows the phase portrait and time histories for omega when it is equal to 26.01 rad per second, which is close to the 2 times of the natural frequency. So Ranjakata and Newton ruptured methods were used for the stimulation of this perturbation analysis. It is found that the Newton rupture method gives a better approximation to the numerical simulation. The calculated numerical error for the Ranjakata method versus the Newton rupture method compared to the actual stimulation was 0.0996 and 0.0419 respectively. So exemplifying that the Newton rupture method is a better fit due to the small error value. So the equations 1, 2 and 3 were solved in the digital computer using the 4th order Ranjakata method. The effect of varying the excitation frequency omega and the initial conditions VB equals 0.1 were studied. And the representative slides show the results obtained. So the phase portrait of the attractor here shows when omega is equal to 26.01, it shows a closed orbit. And this can also be verified through the Poincare map and the frequency domain plot. So further we reduce the omega. So first we reduce it to 21.042 rad per second, and the orbit changes qualitatively and quantitatively, and it is also verified through the Poincare map that it has 2 points and the period doubling bifurcation has occurred. Furthermore, if omega is reduced to 19.4162 rad per second, it again has a period doubling bifurcation has occurred, and this also can be verified through the 4 points on the Poincare map, which satisfies the phase portrait and the frequency domain plot. So now omega value is reduced to 19.37 rad per second. Eventually culminates in a chaotic attractor as shown in the first 3 figures, and you can see that the Poincare map becomes a strange attractor now. And further, if you reduce the phase for omega to 19.37251, the phase portrait shows that it has lost its synchronization. So there are 3 routes to chaos, which are given by torus bifurcation, cascade of period doubling bifurcation, and intermittency. Hence the results from the above figures in summary show as the omega is decreased, the system begins to lose stability and cascades towards chaos. So as the value of omega is decreased, it can be observed that the graphs undergo dynamical transformation, including period doubling solutions, and further reduction of omega leads to chaotic attractor. So now we focus on the topic of bifurcation. So bifurcation occurs when a small change to a parameter value of a system causes a change in the behavior, whether it's topological or qualitative change. So bifurcation can occur in both discrete system and as well as continuous system. So the bifurcation diagram presented in this slide was constructed by solving the swing equation for a specific value of omega when that is equal to 19.4162 rad per second. And by numerical time integration using the classical fourth order Ranjakata method, the forcing R value is incremented slightly and the time integration continues plotting the maximum amplitude. So the R value which we increase is shown in the slide here. And the figure indicates that the initial period doubling occurs just before R is equal to 0.95 and approximately when R is equal to 2.36, the first period doubling in a sequence of period double is exhibited, leading to a chaotic behavior. So these results from the bifurcation diagram can also be verified from the Poincare maps, which were plotted for each R value obtained from the bifurcation diagram. Furthermore, using experiments and simulations, some developed algorithms to find the Lyapunov exponents. Lyapunov exponents give details about the behavior of the system, hence plays a vital role in the analysis. So here the above bifurcation diagram is verified also through the Lyapunov exponents as one of the positive values when R is above 2.1, it has positive values. So the final topic is the basins of attraction. So basins of attraction shows the stable and unstable regions and helps in the analysis of the changes made to the system. So plots show the changes in a basins of attraction when variables are altered, and it is also necessary to consider the boundary condition when studying about the basins of attraction. So initially we consider the basins of attraction for primary resonance, and here the VB1 is varied when the omega is constant. And as the variable is increased, the stability of the system changes. The red and the green color show the stable area and the other colors show the unstable area. And as the variable is increased, the system enters a corrupt state with unstable regions, and hence a further analysis is necessary on the effect of variables in the system and should be considered for some results in future study too. The basins of attraction for the subharmonic resonance is considered in this slide when VB1 is varied. Again, we can see that the system becomes fractal and it enters into a corrupt state. And initially only the variable VB1 is varied when others are fixed. And even when the VB1 is equal to 0, the system is still in corrupt state, and it is due to the effect of theta B1, which is also necessary to study in the future research. So this paper in conclusion highlights the dynamical behavior of the swing equation as control parameters are varied. The entailed work provides analytical methods, specifically perturbation techniques, which are compared with numerical stimulation to verify the validity of the perturb solution for the subharmonic resonance. The numerical analysis for the subharmonic resonance, incorporating numerically the bifurcation diagram, Lyapunov exponents, phase portraits, domain plots, all confirm the appearance of first period doubling in its sequence, triggers chaos, and it should be regarded as a precursor of the imminent danger and difficult operation of a practical system. It is also important to note that the bifurcation diagrams do examine pre-chaotic and post-chaotic changes in a dynamical system. So it is beneficial indeed to identify a pre-chaos pattern of motion in order to understand the chaotic physical phenomena. And the aim of this paper is to complement current literature of this module and utilized in power system, yet gaining a better understanding of the underlying swing equation. In future, we also want to consider quasi-periodicity to understand more into the stability of the swing equation. So some of the references used, and thank you for listening. If you have any questions.